So, in this example, you've been told the function z is equals to x squared plus y squared plus xy minus 4y plus 3 has one stationary value. Determine its coordinates and its nature. How do we determine a stationary point and its nature? The partial differentiation. We start with the partial derivatives. We must get all the 6 partial derivatives. So you'll be given a function z to be equals to x squared plus y squared plus xy minus 4y plus 3. So you can see z is a function of both x and y, isn't it? Z is a function of both x and y. Are we together? So we say where there is z, we put our function f. So the function f is x squared plus y squared plus xy minus 4y plus 3. Function z is the same as f of xy. So what we need is the partial derivative, because this is a function of 2 variables, meaning we do partial differentiation, isn't it? So we start when we differentiate partially with respect to x, we put x as a subscript, meaning we are differentiating z partially with respect to x, meaning f of x subscript is the same as partial z partially with respect to x. We said this should be ordinary, that is partial, that is change, isn't it? Are we together? So in partial differentiation, when we are differentiating z partially with respect to x, it means only x is treated as a variable, anything else is a constant, isn't it? Anything else is only x is a variable. So to denote that, in that z is the same as f, if you want to denote a partial derivative, you put it as a subscript. But if it was ordinary, you put it as prime. It's the derivative when it is ordinary, isn't it? But when it is a partial, you put with respect to as a subscript. So after that, you go to your function z, you want to differentiate your f, you want to differentiate partially with respect to x. If you differentiate x squared with respect to x, what do you get? 2x, because only x is a variable, isn't it? Yes. If you are differentiating y squared, you get 0, because only x is a variable, so y squared is treated as a constant. Are you seeing that? Yes. Then you go here, if you are differentiating xy partially with respect to x, it means y is a constant. You differentiate x, isn't it? Yes. So if you differentiate x, you get 1. You remain with y. Are we together? If you're differentiating negative 4, y partially with respect to x, it means the whole of it is a constant, you get 0, isn't it? If you're differentiating 3, a constant partially with respect to x, you get 0. So it means differentiating f partially with respect to x, we are only concerned where there is x. Where there is no x, are all constant, are all going to 0. Are you seeing that? So it means here we get 2x and here we get y, because y is a constant. If you differentiate x, you get 1. So we end up with that. So you record your first partial derivative, partially with respect to x, you get 2x plus. Now this function is now going to give us 2 more. It is going to give us 2 more. So we now have here f of x partially with respect to x is 2x plus y. So we now use it to get, the first time we differentiated partially with respect to x, the second time we want to differentiate again partially with respect to x. Are you seeing that? So if we differentiate this again partially with respect to x, only x is a variable, anything else is a constant. Are we together? Yes. So if you differentiate 2x, you get 2. If you differentiate y, you get 0, because there is no x here. Are we together? Good. You go to the next one. This function, the first time we differentiated it partially with respect to x. Now the second time, we now want to differentiate partially with respect to y. Are we together? We now want to differentiate it second time with respect to what? To y. So when you differentiate it partially with respect to y, what do you get? 2x, anything else is treated as a constant except y, isn't it? Partially with respect to y, it means only y is now the variable. Are we together? Yes. So here, if 2x, there is no y here, it means the whole of this 2x is now constant, isn't it? Yes. Then if you differentiate y, you get? Are we together? So you go and record that. So we've also found that this partial derivative with respect to x, when we do it for the second time with respect to x again, we get 2, isn't it? The first time it was with respect to x. If we do it partially again for the second time with respect to y, the whole of this now becomes a constant. We differentiate y, we found 1. Are we together there? So we were done with doing it partially with respect to x. So we go to partially with respect to y. Are we together? We now want to do it partially with respect to y. It is this z we said is the function of. It is this z we said is the function of x and y. Are we together? The reason why I'm doing that, I'm trying to avoid such that if you have z to be a function of x and y, if I differentiate z partially with respect to x, I simply denote it as subscript x to avoid writing a lot of things. Are you seeing that? If you differentiate it for the second time partially with respect to x again, I simply denote it as f of x for the first time and x again for the second time, so that I avoid using these long notations. Are we together? Are we together there? Good. Now, we now want to differentiate f partially with respect to. Now, if you differentiate this function partially with respect to y, it means only y is treated as a variable. Anywhere you don't have y is a constant. Are we together? So there's no y here, it means this is a constant. If you differentiate, you get 0, isn't it? If you differentiate this partially with respect to y, you get 2y. If you differentiate plus x partially with respect to y, it means plus x is a constant. You differentiate y, you get 1, isn't it? So you remain with the plus. If you differentiate negative 4y partially with respect to y, you get where there is 4 is where you differentiate, because with respect to y, only y is a variable. Okay? If you differentiate 3, you get 0. If you differentiate a constant, you get. Are we together? Now this partially with respect to y is now going to give us 2 more. The first time we did it partially with respect to y, the second time we now want to do it again with respect to y. Are we together? If we differentiate this partially with respect to y, only y is a variable, isn't it? So 2y partially with respect to y, you get x partially with respect to y, it means it is a constant, you get 0, isn't it? Negative 4 is a constant, you get 0, you are done with that. This function again, for the first time we did it with respect to y, for the second time we now want to do it with respect to x. Are we together? If you do this with respect to x, what do you get? It means only x is now a variable, because we now want to do it with respect to x. Are we together? Only x is a variable, so whenever you see y is a constant. So it means this 2y is going to be a constant when we want to differentiate partially with respect to x, isn't it? So this 2y is a constant. If you differentiate y, you get 0. Are we together? Then if you differentiate plus x with partially with respect to x, you get 1. If you differentiate a constant partially with respect to x, you get 0. Are we together? So in the end, we found that if you differentiate this function partially with respect to y, you had 2y plus x minus 4. Then if you use this function, you do it for the second time again with respect to y, we found 2, isn't it? Then the first time we did it partially with respect to y, second time we've done it now partially with respect to x. Then we found 1. Are we together? So what have we done? We found the 6 partial derivatives. The first 2 will help us get the stationary point. The next 4 will help us determine its nature. Are we together? The first 2 will help you get the stationary point. Then the next 4 is nature. So we are done with this function of z. So the next thing, you now want the stationary point, isn't it? So you say at the stationary point, you know that at the stationary point, the derivative of the curve is 0, isn't it? At the stationary point, the derivative of the curve is 0. So it means either the derivative partially with respect to x is 0, or the derivative partially with respect to y is 0, because it was a function of 2 variables. Are you seeing that? So at the stationary point, the derivative is 0. But here, because we are dealing with partial derivative, either the derivative partially with respect to x is 0, or derivative partially with respect to y is 0. So you go where you have f of x, you equate to 0. So what is our f of x? The partial with respect to x. We found 2x plus y to be equals to 0. Then your f of y you found 2y plus x to be equals to, remember, it is minus 4, then it is equals to 0, isn't it? So if you take negative 4 the other side of the equation, you will get? Yes, so here you can rearrange, isn't it? So the first equation we have 2x plus y is equals to 0. The second equation we have x plus 2y is equals to, if you start with x, so that x is on the same line, isn't it? X plus 2y is equals to 4. Are we together? See, we can use elimination. We can multiply either the second equation by 2 or the first equation by 2. So if we multiply the first equation by 2, we get the whole of first equation by 2. 2 times 2x, 2 times y, then 2 times 0 is 0, so that we can now eliminate y plus 2y plus y. We subtract to eliminate y, isn't it? You can do anything. Even if you multiply the second equation by 2, it means you are now eliminating x, isn't it? You use any method you feel comfortable with, isn't it? To get the value of x and y. So here, x minus 4x, x minus 4x, so you get to negative 3x, isn't it? Then plus 2y minus plus 2y is 0, isn't it? To be equals to 4 minus 0, so it is 4. So what do you get to be x? You divide both sides by negative 3, isn't it? Are we together? So you found x to be negative 4 over 3. So when x is negative 4 over 3, what is y? You use any of the two equations to get the value of y, isn't it? You use any of the two equations to get the value of. So if we use this first one, where there is x, you put negative 4 over 3, isn't it? Are we together? So we have 2x. We have 2x here plus y is equals to 0. You substituted for x, which you found to be negative 4 over 3, isn't it? So what do we get? Negative 8 over 3 plus y is equals to 0. So if you take negative 8 over 3 the other side, you get y to be what? To be 8 positive 8 over 3. Are we together? You found y to be positive 8 over 3. So it means we've determined that stationary point, and you are told this function has one stationary, and you can see clearly we found only one point, isn't it? So this stationary point, a point in the Cartesian coordinate system in the form x comma y, isn't it? So this stationary point, the x coordinate we found to be negative 4, 3, the y coordinate we found to be 8, 3. You were told to determine its coordinates, where we found x to be negative 4 over 3 and y to be 8 over 3. So those are the coordinates we've determined, isn't it? Then after determining the coordinates, then we represent the stationary point. Are we together? Now after representing the stationary point, we now want to determine its nature. Are we together? We want to determine its nature. So how do we determine the nature of a stationary point? So we say, for you to determine the nature of a stationary point, you use the discriminant, and the discriminant is given by the determinant of the Hessian matrix, isn't it? We said the Hessian matrix is a matrix of the second order partial derivatives. Are we together? So we know that the discriminant is given by the determinant. Remember, determinant is placed in those strokes, isn't it? The determinants of the Hessian matrix. Are we together? And if the discriminant is greater than 0, then the nature of that stationary point is a shadow, isn't it? Then if the discriminant is less than 0, then the nature of that stationary point is a turning. So if it is a turning point, then we use the first principle minimum to determine its nature, whether it is a maximum or minimum, isn't it? So here, because z is a function of x and y, if you put z to be a function of x and y, then automatically you will see the first principle minimum will be f of xx. So if f of xx is less than 0, when it is less than, then it is a maximum point. Are we together? Then if f of xx is greater of xx is greater than 0, then it is a minimum. It is a minimum point. That is just an explanation of what we want to do, okay? So can we first see how do we construct an Hessian matrix, isn't it? How do we construct an Hessian matrix? So for you to construct an Hessian matrix, remember Z, you said it was a function of x and y, isn't it? So Z was a function of x and y. So you know a Hessian matrix is a square matrix. Are we together? So here we have two variables, x and y. Are we together? So if we have two variables, x and y, it means 2 by 2 matrix. Hessian matrix is a square. So if you have two variables, it means we have a 2 by 2 matrix. If you have three variables, it is a 3 by 3 matrix. If you have one variable, it is a 1 by 1. If we have four variables, it is a 4 by 4. Are we together? So here we have f, z is f of x, y. So you start. How do you construct this Hessian matrix? So the first thing we do, we've seen this Hessian matrix, it is a 2 by 2 matrix. So you put f, that is 2 by 2. And remember, it is a matrix of second order partial derivatives. Are we together? So you come here and look. The first variable here is x, meaning x will form the first row. Are we together? So it means first row you define by x, second row you define by y. Are we together? The next variable, then we know in matrices you define the row first. So we define the first row horizontal alignment, isn't it? The first row forms the first variable. Are you saying x is the first variable? So it comes in the first row, x. Then y, the second variable, goes to the second row. Are we together? Then you now go and define column after defining the rows, isn't it? So column again, you do the same thing as you've done with the row. Column, the first variable is x. So x form the first column. You are done with the first column. Are we together? Y is the second variable. Y form the second column. You are done with the second. So have you seen you constructed an Hessian matrix? Are we together? A 2 by 2 matrix of second order partial derivatives. Second order partial derivatives. And you can see those second order partial derivatives are actually the ones you have there, isn't it? Are we together? So you now come and say, what is our stationary point? Our stationary point, xy, we found to be negative 4383. So that when you have this second order partial derivative, if it has x or y value, you substitute the x or y value of that point. Are we together? If it is a constant, you just write it as constant, isn't it? So can we now get the discriminant? The discriminant is the determinant. So determinant you put, you see when you put it in box, that is a matrix, isn't it? But now these two absolute value strokes means determinant, isn't it? So it is the determinant of what you constructed here. You had f of xx, f of xy, f of yx, f of yy. So you do the substitution. What is f of xx? F of xx is 2. So if maybe it was 2x, then you have to substitute the value of x, which is negative over 3 for this point, isn't it? Are we together? If for instance you found f of xx will be 2x, then it means it is 2 times the x value of this point you are looking for is discriminant. Are we together? You want to define. Are we together? Good. So there we have. Then what is f of xy? Go there. F of xy is 1. You put it where it is, isn't it? The next is f of yx is 1. You put it where it is. Then the last one here is f of yy, isn't it? Which you found to be 2. So have you seen, you've defined that. So what do you get to be the discriminant? How do you get the determinant of a matrix? Product of the main diagonal minus the product of the other diagonal, isn't it? So this is the main diagonal, meaning it is a product of 2 by 2 minus 1 by 1, isn't it? Are we together? What do you get? You get? So you see 3 is greater than? Are we together? We said when the discriminant is greater than 0, then it is a shadow point. So it means the point, you now come and conclude, the stationary point we define here, negative 483, is a shadow point. It is a shadow point because it implies this is a shadow point because the discriminant defining it, is greater than 0. Are we together there? It is defined by the discriminant which is greater than 0. And when the discriminant is greater than 0, it is a saddle point. And that is how to determine a stationary point and its nature.